From the previous lecture, you studied on powerful functionalities of DBMS. At the same time, it was clearly noted that conventional relational DBMS is not designed for complex data types such as spatial data. In order to fully utilize the proposed framework, you should have a firm understanding of spatial database management system, which is the topic of this lecture. Now, let's start with the question, what is spatial database management system? In other words, what is the difference of spatial DBMS from conventional relational DBMS? Literally speaking, spatial DBMS is designed for handling spatial data, such as vector data and raster data. For handling spatial data, it needs object relational DBMS, in which abstract data type, in other words, user-defined new data types can be managed. Because spatial data is saved, so that spatial DBMS needs spatial query language equipped with spatial operations, and spatial indexing for query optimization, and so on. So spatial DBMS can be defined as a DBMS with additional capability of handling spatial data. Now, let's think about why conventional relational DBMS cannot deal with spatial data. In fact, relational DBMS can handle spatial data, but the problem is it is not efficient. The figure shows the limitation. The cadastral map can be modeled and the data can be saved in relational DBMS. However, the spatial components, polygon, edge, and point, should be saved in 3 different tables, which makes simple spatial operation very complicated because all the 3 tables should be visited using time-consuming, expensive table join operation. So we needed another way to deal with spatial data. One simple solution was so-called dual architecture, in which relational DBMS manage only attribute data, and a separate file system is used for spatial data. It can overcome the inefficiency of relational DBMS. However, the dual architecture cannot provide powerful DBMS features such as transaction management and many others. It could be used for only single user applications. When object relational DBMS was introduced, and it can deal with abstract data types in 1990s, spatial data can be tightly integrated with DBMS. In other words, column data type can be polygon, line, or point. As a result, full functionalities of DBMS can be supported with this architecture. I mentioned object relational DBMS quite a few times already. Let's discuss more about what it is in more detail. OR DBMS can be considered as the middle ground to bridge the gap between relational DBMS and the object-oriented programming, which supports 3 functionalities: complex data with user-defined class, type inheritance, object behavior with method. OR DBMS presents the best of the 2. Consequently, it can deal with spatial data. Among many OR DBMS, object relational DBMS, throughout this course, I will make use of PostgreSQL and its extension for spatial data types, PostGIS, which are open source software discussed in the second week. The example is showing how to create user-defined data type. Address is the case, which is composed of road, city, and zip code. And then using SQL, we can create a table named restaurant, which has a column address. The final SQL actually inserts a restaurant named Spatial to restaurant table. As you can see, OR DBMS can store a complex data type in table, which was not possible in conventional relational DBMS. The figure shows a series of processing in SQL window of PostGIS to create a data type, create a table, and insert a record, which was described just in the previous slide. Now we have a method to store spatial data in DBMS. The next issue is how to retrieve spatial data from DBMS. As we studied it, for the retrieval process, SQL is also used. That means that you need the SQL with spatial operations for spatial data. SQL 3, which is a standard SQL established in 1999, allows to support spatial data types such as point, curve, surface, geometric correction, and operations such as spatial reference, envelope, some Boolean operations of topology, and spatial functions such as distance, buffer, insertion, intersection, and many others. Join operation is to connect two tables based on correspondence check on common field. Join is a key operation. At the same time, a very expensive operation in DBMS query processing. Actually, indexing is to basically speed up join operation. Likewise, spatial join to connect two tables based on spatial relationship is also very powerful, at the same time expensive. In other words, time-consuming operation. Instead of correspondence or exact matching of irregular join operation, spatial join is based on spatial relationships such as intersects, contain, covers, and so on. Let's take a look at an example of spatial join. The query is, what subway stations are located in Little Italy in New York City? For the query, we need two tables. New York City neighborhood table, which is based on polygon, and subway table based on point. The query sets two variables, n and s, to point to the two tables, and then find Little Italy from New York City neighborhood table, and find the subway station of which location is within Little Italy. Then finally return Little Italy and the subway station names. Please note that for spatial relationship, a Boolean function, STWithin, is used for spatial join here. The figures on the side illustrate the query processing and the result of the query in table view and map view. I brought in another example of spatial join. The previous example was spatial join between polygon and point. This time, it is between polygon and line. The query is, what are the rows which cross the boundary of Corona neighborhood? The SQL is similar to the previous one, but this time the spatial relationship is defined by a Boolean function, stcrosses. From all the streets of New York City, the query retrieves only streets which meet the boundary of Corona neighborhood. And now you are looking at the query result in table view and map view. Now let's think about the same query with different data set. The query is, what are the rows which cross the boundary of Dane County in Wisconsin? For the query, we are using county map and road network of the whole country. For the query, all the roads from Alaska to Florida should be checked if they meet the boundary of Dane County. How about that? Would it work? Yes, it works. However, it will take a lot of time. That's why spatial indexing is required in spatial DBMS. For efficient query processing of the previous spatial join, what if we have to check the rows only around Dane County in Wisconsin? the query processing can be done very quickly. Spatial indexing is to provide a better search performance of spatial context. For that, R-tree, which is an extension of B-tree, was introduced. There are many other spatial indexing methods, but R-tree is considered as the standard. Additionally, it's worth mentioning geohash, which is a powerful method for spatial data searching and organization, which is going to be used in spatial big data. The figure is composed of points and rectangles. For the given spatial data, you can apply R-tree based on MBR, which stands for minimum bounding rectangles. You are looking at the given spatial data set, which are organized by two different levels of MBR, M, N, O, and P. Represent 4 higher level MBRs, and each MBR has 3 or 4 lower level MBRs. For example, M has A, B, C, D as a lower level MBR. A hierarchical structure can be transferred to tree structure, as you can see now, which is R-tree. Similarly to B-tree, it stores data sets on the leaf nodes, and it is a balanced tree. Quad tree is another spatial data indexing method. As you can see the example, quad tree partitions 2D space into 4 quadrants recursively and save the data to the end nodes. The figure shows the corresponding point region quad tree. Each node has exactly 4 child nodes, and the data is saved to the end nodes. Which one do you think is better than the other, R-tree or quad tree? Of course, it depends on your spatial data set. Generally speaking, if you have unevenly distributed data sets, R-tree would be better because it can balance the shape of the tree structure. On the other hand, if you have evenly distributed point data, quad tree would be a very good choice. Now let's take a look at a real example of applying spatial data indexing and its performance. The given query is, what are the name of the roads in Manhattan that is more than 30 feet width, in which ST-contain function is used for spatial relationship for the spatial join. Without indexing on the left and with indexing on the right, the difference of the query performance is 47 seconds versus 1 second. It is a significant improvement. What if we deal with the road networks of the whole country, the US? The difference will be obviously phenomenal. Now let's see the difference between GIS and spatial DBMS again. We discussed it in the second week. GIS has a variety of spatial data handling capability, but only to a certain degree. SDBMS, spatial DBMS, is basically designed for spatial data management with all the wonderful features inherited from conventional relational DBMS. In this lecture, we started with the definition of spatial DBMS, and object or relational DBMS was introduced as a DBMS solution for complex data types such as spatial data. SQL for spatial data and spatial join was discussed. Finally, 2 different spatial indexing methods were introduced, and performance enhancement with real example was given for your understanding of the value of indexing method. All right, this is the end of this lecture. See you all in the next lecture.